morning to all of you. I am Dr. Anupriya Jha, Assistant Professor in Department of Mathematics, Dayanand Sagar College of Engineering, Bangalore. I welcome you all in this AICTE Atal FDP on Computational Mathematics and Artificial Intelligence for Engineers. It is my privilege to introduce today's speaker, Dr. M.P. Ramachandran sir, fifth day of the first session. Dr. M.P. Ramachandran sir obtained his PhD in mathematics from IIT Bombay. His research interest was numerical solutions of integral equations with applications. Then he joined Space Application Center, Ahmedabad. And nearly a decade later, in 1998, with ISRO Satellite Center, Bangalore. In ISRO, he has contributed in the design of a shaped antenna reflector with high efficiency and feed systems. He has developed attitude determination algorithms for various ISRO missions, including a quick Earth pointing recovery for GEO satellites. This approach is novel and has been transferred to other space agencies. Image motion compensation and formation flying were other new activities carried out. He was the deputy project director from ISRO. He was the deputy project director of Aditya Satellite. He has given talks on flight dynamics at ISRO on many occasions. He retired from ISRO as a group director of Flight Dynamics Group. His interest in computational mathematics related to integral equations, differentiation of noisy data, and oscillatory integrals. He has many technical publications and has contributed as a reviewer too. He has also contributed for articles in Popular Science magazine. Now I request our HOD to say a few words about today's speaker. Over to you, ma'am.
Yeah, thank you, Dr. Anupriya. A very good morning to sir and all the participants. Sir, on behalf of Dayanand Sagar Institution Management and on behalf of AICT Atal, I extend a very hearty welcome to you on this fifth day of our FDP. We are really looking forward to listen to you, sir. We have been waiting for this session for a very long time. So without taking much time, I welcome you. Over to you, sir. Please take over. Ramchandran, sir, are you able to hear me? Yeah.
Able to see my screen?
Yeah, I can see the screen, but your voice is very low.
Can't help it. Okay, let me. Now is it okay?
Yeah, it's fine, sir. It's fine. Perfectly fine.
Okay. Yeah. Thank you very much for inviting me to speak on a topic in this Atal program, which is aimed in training and learning and also exposing the application of mathematics to useful and engineering problems. Actually, the idea is very nice. That particular line I liked very much because mathematics is useful when it is applied, and we can make out what are the intricacies that are involved, exactly like the lecture which we are going to listen today, which I did some time back. And this work is not associated with my regular activities in ISRO. And this is different. And I hope it is useful. So ours is the last day and mine is the first lecture here. I retired as a group director of Flight Dynamics Group. One sentence I have to tell is, Flight Dynamics Group is involved in orbit determination, orbit modeling, attitude determination, and maneuver planning. These are the activities which were coming under that. But anyway, the topic of today's lecture is numerical differentiation of noisy data, and it has some applications also we will see. Basically, before going into the subject, one has to look into mathematics. We have to structure it such a way that any given lecture should have a particular format, looking into it analytically, what are the issues with it, what are the applications associated with it, how do we solve it, and it is a very scientific way we have to go about it, especially in mathematics. So here from this title, when I see the numerical differentiation of noisy data with application, first let us say what is differentiation. This is a very well known fundamental brick of the edifice of mathematics, differential. We generally take differential analytically, and if it involves complicated functions, we time to use some numerical method. But first of all, the differentiation should exist. So with all the time ambit precautions, we go into differentiating it. Now, first let us consider the data is we are collecting is true data. Okay. Now, a normal world is not an analog world. It is a discrete world. So the data is available only at certain sampling intervals. I will explain in the course of the lecture how it happens. That's the engineering aspect of it. So let us assume the data is available to us and they are all true. Then there is a global and local approximations which are involved. What is a global approximation? We all know that. Global approximation is a Lagrangian interpolation. Like what I have shown in the slide, fx is represented as a Lagrangian interpolant and corresponding to the points where we have the data. That is fx xk here. Now, the derivative can be easily obtained. Now, but actually, although it looks very difficult, but on a code, it is just you have to do some coding skill is there. We can always make the derivative very comfortably. So what it does, basically, we are fitting a polynomial which passes through all those points which you can see it in the plot. But there are some associated issues with it, even if you call it the higher degree polynomial, it has Gibbs effect at the ends. I'm just putting it as across, although it is not related exactly to our field topic. And what about fitting other polynomials? Well, there's no use because a polynomial is unique. So whether you use a representation which changes, the value will be the same. So taking the differential, we can find out what is the value at a given point, right? Now the point is, this is a true data. There is absolutely no noise in the measurement value of fxk. They are all very true values. Now, local fit also is there. What do we mean by local fit? Local fit is, for example, you can fit it with a between two mesh, in a mesh between two nodes, we can fit a linear line. Okay, line we can fit, or we can have a parabola, which is a quadratic, or we can have a cubic spline. Now, these are the effects which we can use. For example, if you fit with a linear, then what happens is the derivative f dash, which is given in this slide, is given by fxi plus 1 minus fxi by xi. This is nothing but the slope joining the line between the values of fxi plus 1 and fxi in that interval of xi and xi plus 1. This is a very simple formula. Now we are not attempted any data with a noise. We are still in the world where everything is true. Okay. Now I will also show you what happens when we are using spline. This is, I have extracted all my presentations are taken from some literature or anything. So I have not hardly written a few of them here and there. Okay. Now this is I have taken from an Alberg book on splines. The polynomial S delta X is basically a cubic polynomial interpolating in the interval xi and xi minus 1, xj and xj minus 1, as it is mentioned here. Now, you can see some new factors apart from yi plus 1 and yj plus 1, which are the measured numbers, values at those points. There is some mj minus 1 and mj also occurring in this expression. X is, you can see there is a power of 3 is there because xj minus 1 x whole square and x minus xj, it makes it a cubic polynomial, right? Now, what is this new appearance of these parameters mj minus 1 and mj? Well, they are nothing but let us assume that is the slope at those points of the function, which we don't know. Now, what happens is the spline actually, when we will come to know more of it later, when you assume or set that there are second derivative is continuous, then you get a certain conditions. These constraints translate into certain set of equations that is given below, like lambda j mj minus 1 plus 2mj plus mu mj plus 1 is equal to. These are all known constants. Lambda and mu's are all known constants. So it is in terms of yj minus 1. Now the measurement is true and the measurements are yj minus 1, yj minus 2, like that we are having. So the condition is these conditions along with certain end conditions, which I have not written here because a lot of them. I'm just trying to give the concept. It helps us to solve m. That is, m is nothing but our first derivative. So directly when you are fitting a spline, not only the accuracy improves, it gives you the derivative directly. So that is one advantage of spline approximation. Now all this so far we have got the data in a very ideal world where yj's are all measured truly. They are all as they are. There is no noise which is introduced in any form. So that is a kind of system we are. Now, what happens actually in the world is no instrument which can measure any value can measure accurately or truly. There will be some noise. Now, what are the noise effects? Electronic noise. There will be an optical noise if it is an optical instrument. So if it is an electromagnetic instrument, microwave, anything, whatever it may be using, there will be an associated noise with it. There could be a time noise at which we are sampling. So many things are there. We will see some more examples later. So our values are measured and discrete, and we have a noise. Now, one simple example we will take, which is analytical. Now, you can see on the right side, y bar is equal to y plus epsilon. This fellow epsilon is our noise. How it is in the form of some sigma into sine of all that. Now, sigma is our variance. Okay, that's how the noise is occurring. Noise is a statistical phenomenon, and any system is characterized with sigma as being its noise. Normally, if you see any instrument, finally they will ask what is the sigma of it. That is what's the accuracy of that instrument. It can be very good, but it has prone to certain error of so and so. Now this sigma is what is it? We are putting it as y bar is equal to y plus epsilon. Epsilon is characterized by this. Now you take a differential. Now what happens is we have a y which is a true value. After that, that derivative gets derivative of epsilon is there, which becomes 2 pi by sigma. Now you all the listeners can make out when sigma goes close to 0, what happens is this right hand side second expression, it starts going to infinity. Now a norm is normally used to judge what is the difference. A norm is a measure and it usually is a distance measure, which is a uniform norm as we call it. So when we say y bar minus y, which is the norm of what is the max is sigma, that is the maximum here. Here it is denoted as sigma is not variance, but it is the max of that number. Now what happens is when it goes to 0, you can see y dot minus y bar dot. That is a true value minus the measured value derivatives, the difference in the uniform norm is 2 pi by sigma. When sigma goes closer and closer to 0, it starts going up. So what it means is a differential of a true value with the noise. When you take derivative, it is susceptible to some issues. So we have understood analytically there is some issue associated with any value associated with that noise. Now we take up another case because one is not enough generally. We have a G which is equal to F plus epsilon into sine of, this is the net. Generally this form is, you can see, a very common parlance in any engineering because the noise will be will have a sinusoidal pattern within itself. Now G is our total measured value, whereas F is a true value. Now when you take again G dash, you find G dash is equal to F dash plus omega epsilon cos of omega x. Now all the listeners should be knowing that epsilon also, if you keep it constant, some number, omega is can be any number. Okay, if it can go from big any number. So what will happen is it need not be a uniform number or steady number or anything like that. It can keep varying. It can be large, it can be small. So basically what is happening, what we understand from this is, basically when you differentiate a function which has a noise, then what happens is the noise factor doesn't allow you a stability. Stability is a very important tool in mathematics. Anything which is done, it should be stable. It is not that next moment it becomes something else. It should not be like that. Now, what is basically a noise? Now, noise is a part of any experiment data and measurement. Every instrument, electronic instrument, has an integration time. Integration time means it has a measurement, then it has to take the data and it has to put it back through a circuit or something. Or you can call it as a response time. The system has to respond to that. It has to collect the data. It cannot be instantaneous. For example, a human being is a very good machine. That way, we have some number of frames per second. We are able to make continuous motion. So like that, but that is exceedingly good. But instruments are not that efficient. They are closely becoming efficient now. Now, and moreover, because of this sampling and an integration time and a polling time, all these are all a part of an instrument structure. So it becomes discrete. And this electronic noise, basically it is a Gaussian nature. I will come to it, what is a Gaussian, next slide. But basically, again, I want to inform here that an instrument doesn't gather everything in a one particular frequency. There is a bandwidth which it collects. Generally, you might be knowing any instrument has a bandwidth. Now it operates in that bandwidth. When it operates in that bandwidth, the noise is called white noise. That across that bandwidth, it exhibits the same power. So generally, systems follow Gaussian noise, and they are also white also. That is, if you take the power across the frequency, the power of the signal will be the constant. That will not be changing with respect to the frequencies. It will be uniform across all the frequencies. That's how that instrument is designed. That's the ideal instrument. Okay, let us discuss about that. Now, this is a Gaussian noise. I think many may be familiar with this figure. There's a normal distribution. That is with respect to time. The error or plus minus epsilon. So here is one arrow mark I have put. You just observe there's a top of it, there is one x squared. This will be very useful later. So this is how the distribution is. And the mean is generally 0. If not, there is a bias in the system. So electronic systems generally have a bias that can be always co-opted into the system, no problem. But what is important is on and above the bias, there will be a noise. So we have now understood what is differentiation, which we are familiar. And we also found out that when a function is there, and if it is having a noise, and you try to differentiate, differentiation leads to there is instability or the stability is lost. And now we saw also that What is a Gaussian noise? Which is a noise which is generally present in a electronic instrument. Okay. Now, to get a feel of this is a very famous photograph in image processing. The left side photograph is a true photograph. This is a photo I given here because this author has created a noise, a Gaussian noise. On the right side, you can see it is a noise image. Sorry. The idea to tell this is in a gray scale from white to black. Now noise has been added. So what happens when an instrument is having noise? So the left side is also having some noise, but it is so good that it is looking noiseless. The right side instrument, the photograph is having noise. So we can understand what is a noise. Now, here is a function, some function. We will come to it slowly. We will see this develop, this one as it develops. There is a function. Actually, it is a V-shaped function. That means it's one which is not so conducive to differential, but let us see. It has a derivative to be found out, but there is a noise. Originally, the original function is of V-shaped, okay? That you keep in mind. On the top of it, there is a this one. So analytically, we investigated and we found any time in mathematics, before numerical mathematics also, one has to resort to numerical mathematics after understanding the canopy of analytical mathematics. Any mathematical modeling we do, we are doing it and we analyze whether the derivatives exist, all that, and solution exists. That is the scope of knowing whether the solution exists. Now we have come from that frame, if and found out analytically also there are issues, then we are now solving the problem numerically. So one of the simplest thing which we have adopted earlier, we have seen also, is f dash fit with a linear, piecewise linear function, and the slope is given by, this is a very common thing, the tangent formula. Now we take the derivative, this function with a noise. We are trying to use this simple slope formula. What happens? You see, this is what is happening. This derivative is becoming like this. Now, what is the meaning of this derivative becoming like this? It says, the other says, this noise is getting doubled. So the difference formula, which is the simplest formula which we can use, because most of the systems where computational time is very just very difficult, linear fit is the best, and we use this f dash. We find that it is almost doubling. The noise is earlier noise was something, now noise has become more, double. Now, but why the noise has doubled? We make a query. Now, here we go. This is slightly, we have to be very careful in understanding this slide, because this is an analytical investigation. Now f dash in the top, you can see, is nothing but 0. We have got values on fh and f minus h by 2h. Okay, fine. Plus all this. Now, how do you get it? fh minus fh by 2h is my, this is all Rolle's theorem only. I think all of you can be familiar with that. So my measurement f of h with a cap is equal to fh plus 1 plus theta 1 ef. That is kind of my function is corrupted with that kind of noise, where theta is argument is less than 1, and f of minus h is equal to f of minus h into this. This is another at minus h. This is a kind of behavior it is there. So when I take the these two effect of noise line, f of cap h minus f of cap minus h divided by 2h, supposing I do that, and I do it on the right hand side also, that is fh minus f of minus h by 2h, then the remaining part is also there, that is theta 1 epsilon f and then theta 2, all that. Then I adopt that Rolle's theorem which I have written in the top. I use that. Then I find that it is 2 phi epsilon f f psi by 2h. Now what it means? Now you can see that phi is less than 1 and epsilon is also 1, but this character 2 has appeared. So what is happening is this noise which was originally F kind of source. Now this difference is now showing 2 times 5F. Now, so the what is happening out of is the noise basically by applying this linear kind of fitting is basically doubling this. This is an analytical investigation of the previous problem. So we have seen that differentiating analytically or a simple numerical technique creates a problem. One, it is first of all not stable. Second is a numerical application just like that, without understanding anything. If you apply, it is leading us to more error in the differential. Now, this is what it is all amounts to say is, if y is my true measurement and y cap is my measured issue, and epsilon is my measurement error, then I take a differential y dot minus y dot cap is equal to epsilon dot. Now, what it means is the noise is actually differentiated. Now, what is the meaning of noise being differentiated? The noise is blowing up more. So there is a problem. This noise is getting amplified. So exercise of straight away applying whatever we know, read in books, which is applicable for numerical methods, for as though they are given in a very nice world where all measured truly, that is blowing up the problem. So the real world application where measurement or how it is measured, Y's and F or whatever we have, these symbols we have used, right? This is blowing up the issue. I hope you are able to see my next slide, right? This is, all of you must be very familiar with this photograph. It appears in most of the cricket matches which you see. Then this decision is taken by this one. Now, what is shown in the red is actually a measurement. Okay. Now, the arrow mark, pink arrow mark is pointing to that point where it is, this figure is clearly seen. Okay. Right? Madam, this, okay. Then we are having that gray path after that, the blue path, which is after the impact, the umpire has to make it out from the camera, decide whether it is going to hit or not. Now, what is the meaning of this problem? See, the problem is why this derivative is required. This many people will be seeing all this scene. We are talking about velocity. That is, we have to find out the velocity and not the speed. We have to find out the velocity of the ball through the direction. When I'm saying velocity, I'm talking about a vector. That is, all the direction cosines of that vector are important, right? And the unit vector also you construct, no issue. We have to know the velocity and its components properly. Now, what is this? Why I am proposing this problem here? Very simple. This is the Hawkeye which is used. There are 6 cameras on all the sides, and it is sampling at 1/100th of a second the moment the ball leaves, and then the entire thing is constructed from each direction. You can find the motion based on the ball being tracked in the image. They construct in the frame of that ground how the ball is moving. Okay, so the position of the ball is used, and then finally at the point of impact of where the pad is, we have to construct the velocity. from the position, getting the velocity is nothing but the derivative. So, and all the instruments or optical instruments, okay, they have their own noise sources, because no instrument is paka actually. It cannot be 100% correct. There will be a camera accuracy will be there. There will be a time error. There will be quite a number of other errors also. So all these small errors can contribute. So this is one of the problem I'm saying. Why I'm putting up this is it's a popular problem. So we can see that it is sampling is discrete, and there's the instrument has a noise, and this is how it is. By the way, what we see generally is not more frames. When they go for an appeal, then they use more samples, and they use better sampling distances were smaller, and they were able to do it better. That's how it is generally. Now, this is one we saw is a popular application, but what happens actually in high-end technology or satellite technology or something like that, if you see, we have what is called orbit determination. How it is done? Now we measure the Doppler from a ground station. We see the satellite. A signal is sent, it goes up and comes back, and there is a drift in the Doppler that is kept with them. Now that is used for orbit determination purposes. So the ground antenna is a one which is measuring the two-way distances, or it can be measuring two-way distances, or it can be measuring the Doppler also. Okay, let us leave all that. But the point which I want to tell is, the position is known, or the velocity variation is known, whatever it is, to construct finally the entire orbit. But associated with that station, there are various errors. For example, there could be onboard oscillator stability, miscellaneous additional sources such as troposphere, transit time error, time tag error, resolution error. All these amounts to a random noise and a bias range of 0.9. Our bother is not about the bias, but about the noise, namely 0.9 meter. So even in if you do a ranging, there is an associated error in the measurement of equivalent to about nearly a meter or so. It is there. So it will not vanish. Okay. Now, finally, what do you mean by knowing the orbit? Orbit is determination why it is carried out. Orbit determination from the position. We also should know the velocity, but the velocity should be very accurate. Why it is to be accurate? Because supposing you are going by bus and you know the speed of the bus, average so far whatever he is going, and you know your initial position, now current position, and when you want to reach, let us say you want to reach Tumkur, you can make out with the present speed what speed he is going up to Nelamangala. When he will reach Tumkur, you can make out roughly, you can make provisio, your speed calculation is correct. Similarly, in orbit determination, what happens is unless you know the velocity, you cannot use the orbit model further and propagate. These are all very, very important words. Once you know the velocity at a particular point, you should know the you given the time when it will reach moon, when it will reach Mars, when it will reach, or it is going around the earth, when it will go over the next ground station, when it can be tracked, and another event you planned. So these are, so the velocity from the position is equally important. We saw some popular, this one, we saw one technical activity also. You can see a plot below that the velocity, the pink line shows which direction the velocity is. So that is the direction called along track. You see here in this plot, what is happens to the along track. The along track has a secular deviation, whereas the across and normal, that is a radial direction, that is from the earth towards the satellite, that direction is not so, it keeps constant. or away from the plane, which is called normal, that is also not an issue. But along track, with respect to time, it starts climbing. Why? This is a plot from a book. Why it happens? Because whatever you do, there will be an uncertainty in the velocity. No, velocity, because velocity cannot be measured directly. That is the uncertainty principle. Only position can be measured. So velocity, there is a derivative, cannot be measured. Now, so we have to estimate it, but still there will be some error in it associated due to the instrument which is measuring it, the position from which we differentiated and we get it. So that velocity will slowly start climbing up. Error will start building up from that true value. So what I found out is we saw analytically any function which is having a noise is unstable when you differentiate. Numerical schemes cannot be adopted straight away. And there are applications which we see, which helps us the use of taking a derivative when there is a noise in the position measurement or the noise is there in the position which we measure. I hope so far everybody have understood this. Now, I think, yeah, this also we have seen. Yeah. Now, what is we'll come to a topic which is called, which is very old, 100 years nearly old, by Hadamard, when he defines what is a well-posed problem. The well-posed problem solution exists, it should be unique, but the third point is very, very important. That is, as the input changes, the output should be reasonably stable. So it should not vary like what we saw, that sigma varying or epsilon varying, some examples which we saw, like here, where we have a small change in omega, then what happens is the derivative starts blowing up. This is a no stability criteria. Now what it means, this problem is not well posed by the definition of Hadamard, which is almost 100 years old. Now, this came to light. Now, is this all enough? Example which we looked is enough? No, I am not satisfied. I will take up writing, say fx. There is nothing wrong in writing fx is equal to f naught plus integral 0 to x u of s ds. This is nothing but a Volterra integral equation. That is, if I differentiate that equation, I get f dash is equal to u simply, because that f naught is a constant, it disappears. And therefore, you take a derivative under the integral sign, you will get f dash equal to u. So what I am told here is to take the derivative, that is f dash, and finding u, the equation which is in the top, that is fx is equal to f naught plus integral us ds, that is finding out u when f is given is nothing but an Volterra integral equation. So why I'm writing like this? Well, there is a reason. This is from the solution of ill-posed Volterra integral equation by Patricia Lamb. Now what she says is, all it amounts to saying is, that is, if we have a Volterra integral equation, which is there in 1.1, where A is given as an Volterra integral equation, K is a constant one which satisfies the Volter condition. What it all amounts to is that 1.1 is an ill-posed problem. So we already had a good smell that the differential or analytically, that a function which has a noise, its differential is no stability. When we convert it into a Volterra integral equation also, we find, yes, it has some issues. It is not a well-posed problem. It is an ill-posed problem, correct? So the differential business is a ill-posed problem. Ill-posed problem or an inverse problem. Inverse problems are generally ill-posed. Now, what are the cousins inverse problems? For example, this, I think many may be aware of it. That is a CT scan. the patient getting into it. There is a one direct problem is given the patient inside, what is the scan is looking. But the real problem comes is, given the CT scan image, what is the person's internal capabilities? This actually, the scan mechanism goes in, see, taking a CT scan by that electronics, whatever associated with it, it is not a very important thing. But along with the CT scan report, generally one gets inferences which are there. Now those inferences are purely mathematical only. That's an inverse problem. So we'll come to know that problem is one direction is easy. But to get to know this, here you can see again that over R and over theta when it comes, then if you take the integral the other side, it becomes a differential problem. Okay, this is one thing. Second is, this is also related to my field, namely when you are having an orbit with a given gravity. But once you know the orbit, how to determine the gravity, which is called gravimetry, which has been carried out. That's how the NASA people are able to get the gravitational fields of Moon, Mars, forget Earth, they did it long back. So we are using only that. So basically this potential of gravity variation, which you are seeing in that figure, is one place which is red is having more gravity, whereas yellow it is less, then blue is much lesser gravity, because you can see continuously it is varying. Gravitational pull of the earth is not uniform as it's assumed. They have found out that inverse problem, which is called gravimetry, is also an inverse problem. Is again, it involves derivatives internally that I don't want to get into it. I'm just touching up. There are applications where proper applications where you have this derivative in the inverse problems. Okay, these are other applications. This one important thing which is you can see here, you can read it out, which I have extracted from the literature. All this. One is the oxygen intake and the metabolic or curative, which is related to COVID also. All these things, when you take the oxygen which is consumed, and how the metabolism is always sometimes a derivative of it. So it involves some derivative. So the rate at which the oxygen intake is taking place. So if you see all that, it does have a wide spectrum of applications, especially in the control systems, where you have most of the times the Jacobian matrix is used and partials are undertaken. So you will find this requirement of this one will be happening. Okay. Now we are coming to more mathematics. That is Ax is equal to B. We all were very familiar. Now, if the we are having now here some noise. Now, if supposing A is of rank n, then you know very well X is equal to A inverse of B plus epsilon. Epsilon is a noise, so it is all solved properly. But the second, below that you can see where we have more number of solutions, more number of equations, less number of solutions, and less number of equations and more number of unknowns. That is respectively denoted as over and under. We have the solution. Now the one which is marked as pink color over, it is a common occurrence in orbit determination. That is, we have the state parameters, position and velocity, x, y, z, x dot, y dot, z dot. But we have so many measurements from a given station, so many stations to be used, all that clubbed together, then generally this is how it is obtained. That is, what we have done, this is nothing but the it's a least square sense we have found out here solution. Okay. Now, what is a least square minimization problem? We are coming slowly to it. We are first coming to smoothing a problem. That is, a Gaussian noise is there in many applications. Now, what happens is Gaussian noise, which we saw on x squared when we described the Gaussian noise, that x squared is what is E transpose E. So the maximum likelihood function in a Gaussian distribution, which we saw one expression, x squared. I hope you people remember it. That expression we are trying to minimize. There it should be maximized, which becomes a minimizing problem, minimizing this effect. Now, least square is made for any system which is prone to Gaussian noise. That is the first thing we have to understand. Now, sequential filters are all there. I am not getting into anywhere near that because that is another big motion and I am not very so familiar with it to talk on it. Next. Now, when I say least square, so I have given you a scope that given a problem which has some discrete measurement, because the system of equations, therefore discrete measurements are there. There is some epsilon. This is how we can solve it. This is in a least square sense. We have smoothened it. Now, one approach over, then Kalman filter and all, etc. I am not interested because they are more prone to useful for real-time applications. I have what is called the Savitsky-Golay filter. Now, what is this filter? This is a very interesting filter. Somebody can go through the literature. It is a moving window kind of filter where the like an interpolation, least square doesn't go through all the points. Okay, now all the measurements. It will only fit over the measurements. Whereas this will go over those ordinates, okay, and you can tune it to the polynomial you want over the number of nodes. If you suppose the number of nodes you take as k, the polynomial can fit is k minus 1. N can be k minus 1. Now, this if you go to the literature, these coefficients are all fixed if it is a uniform. And it is a moving window where 0 is the one which is in the center of that window. And on either side, there are n or n. So it is 2n plus 1, kind of 2n1 plus 1 kind of thing measures. Normally, some 7 is used or 13 is used. They are very ideal. Now, when it goes like that, this is a very beautiful filter that it is used in many applications where derivative was required and where the measurement starts improving as we approach the target. Namely, for example, a landing mission where altimeter is there, but we want to find out from the position, we have to find out the velocity. There, these kind of filters are very commonly used. Again, as you see on the right hand side, I have written sigma. It is basically a least square only. Okay, right. Now, this is, you can see how this I hope you are able to see slowly that window is moving. It is taking some 3 samples at a time. It keeps moving over that entire domain. This is how that filter goes, right? I hope that animation is coming. That is the full samples. This person is going over that place. Okay, that's it. Now, as touching it, we can also say that Fourier series is in a way least square smoother only. That is, this SG filter or Fourier. Only thing is one does whether the SG filter with a polynomial or a Fourier series. Whatever we are fitting and then they are taking derivative. The engineering application of it, one has to do a frequency response or whether any phase delay is introduced by the fitting or polynomial which we have used. So whatever we have done so far, we have done essentially we have smoothened the noise. That is, we have taken 1 second. The right hand side you can see sigma of, that is the polynomial which we fit, and the true function and the function which we are approximating. That is a measurement here we are doing. The error is as you see in the first line there, 0.5 epsilon transpose epsilon. That is we are trying to minimize. So what it means is in the norm which I told, in the sense that distance between the measurement and the one which we are fitting such a way that the norm, if I define, if I take this 0.5 epsilon transpose epsilon, where epsilon is the band of my noise, it is trying to reduce that this one. Epsilon and epsilon transpose, why? Because error can be both plus or minus. Generally, as in Gaussian, which we saw, mean is 0. So it is only smoothing the noise. Okay. So what we have done, anything, nothing so far, whatever we told that as far as the derivative should be good, that we have not targeted. Actually, so far we have not targeted. I will recap one more time. We saw analytically when there is a noise, there is an instability, numerical schemes cannot be adopted very easily, and we found out the least square method can be used, and it approaches in solving the problem also we have seen. That is a smoothing techniques. But we have not attempted anything or has not assured anything about the derivative. Now, what is the meaning of this? We will see now. We are taking smoothing with a cubic spline. I hope people, after listening to this lecture, go and see some books on cubic spline and smoothing techniques. Especially, they are very old, but they are very novel, in fact. Now, first line, the Carl D. Boer Practical Guide to Spline is an excellent book. It outlives, I don't know how many times it has been cited. And even other applications were coming out of it, B-splines and all, how many, they are all cross thousands citations. Excellent piece of literature it is. Now, when you see the top one is basically what we have attempted, that is a measurement and the fit GXI, we have square of it, we are minimized. Now, this is ensuring us there is a reduction in the noise and by the fit. Now, we are added now one more. What is that? That is G double dash Xi dx, that is also minimum. What it means? It means the derivatives or the second derivative if you take, the derivative which we compute out of this fit G, that is smooth. The curvature is ensured. The minimum means it is the transition between G dash at one point and another point, they are all very, very smooth. That is what we saw in our problem once. Once we take derivative, it was doubling. So this condition is new. So where the motivation is coming, this is all not coming out of hat, but this is called what is called the draftsman's spline. There, when you fit it, they fit it, that they find that when they take the shape of that flexible wood piece, which is called also a spline, when they shape it such a way, which is fitting the points which they want to connect, they find this one which has a this is how that shape is, so it ensures the same condition. Okay, now when we combine these two things, namely the summation, which is there only in least square, but we take that and we add the smoothness constraint together. This is called a Tikhonov regularization parameter. Okay, now what is that parameter? P, that is how you add this smoothness condition. One second. How you add the summation, that is a smoothness, and that integral, which is the the first one is a noise, the second one is smoothness. How you add depends upon what is the value of P. Now, how do you get this P? Now, that is exactly the problem of the numerical techniques which involve numerical differentiation when the data has noise. So that is a problem which we are attempting. So far what? The strategy which I adopted in presenting, looking into analytical, looking into raw directly, all this should be adopted in any of the activities when you take up in computational mathematics. Need not necessarily be to this pertaining to this subject. Okay. Now, let us see what the beauty of P. Now the data, I hope all of you can see the blue dots. Now that's the blue dot is our data. Now supposing I take P is equal to 0.05. I go back to my previous thing. P is 0.05 means I am giving very less weightage to the noise, but more weightage to my smoothing. So it is very smooth and it is like a smiling lip. Okay, fine. Now P is equal to 0.5 I make. Then this, you can see the scattered points of the blue, and this fellow has slightly improved in reducing the noise, but this curvature is also maintaining. You see the one important thing here in the left side, 0.05, how beautiful that curve is. Its derivative, if you take, it will be very smoothly varying. So the second derivative condition, that is namely integral of g double dash, has worked out so very well. It is very smooth. Now, slowly we have taken a midway point, 0.5, for half of our smoothness, half for noise. Then we have 0.75. You see, now it has improved more. The noise level has come down more, but the smoothness has slowly got affected. And when you make it 0.95, that is, it's more of noise and less of smoothness. Slowly you can find derivative discontinuities are happening at the points where where it is turning up, like a U and a U on many sides. Okay, so the derivative is slightly getting affected. So you can see how that parameter P is affecting the noise control as well as smoothness. This is a very beautiful example. So regularization, once you input it, what all it gives? First, it makes the problem stability is there and it guarantees well-postedness. Now, basically the algorithms, they all involve about how do you find P. So the various algorithms are there in finding what is the value of P. Okay, now P, there are techniques, there are several papers. I don't want to get into that. Everybody who is interested in this kind of field, they can pursue on their way. But I'm informing some of the class, what you call something which I found very interesting. Is a DeBoer's approach, which is nothing but Scobens and Range classical work, which is there in your book. Or you can use the cross-validation technique of Craven-Weber. Now, what it means? It means supposing the noise statistics is not at all known. Sometimes it can happen. The instrument we may not be knowing. We just got the data, measured data. Somehow that we have been told we have to fit a curve and also obtain a reliable derivative. Okay. Now, how do you go about it? Then we have to adopt those approaches. Supposing we know the instrument and its sigma, the variance, etc. are known, then we can adopt what is called discrepancy principle, or choosing the value P to be the variance itself. Okay. That is the parameter P can be variance of that this itself. We will see all that. Okay. Now we saw this, I think you can remember this case where the noise was simply doubling. Okay. Now, when you use a smoothing technique, simply you adopt one smoothing technique. Okay. Correct. Then it is simply denoise is alone done. Still, if you see the obtained differential is not good. It is not very nice. Okay, there are some jumps here and there and all. But when you use a regularization technique, especially when you follow what is called discrepancy principle of Morozov, if you adopt that approach, then what happens? Miracle. The derivative is basically a step function. It was hidden all these times. So you see a numerical technique with, especially when the function is having noise. When you take derivative, you simply adopting some technique of smoothness also will not help. You should use appropriate judgment. As we saw here, there is a combination of noise and smoothness together. I have to use. How this P is chosen in this particular example, this example has used what is called, it has used, we know the measurement noise. Based on that, this discrepancy principle is used, and when it is adopted in finding the numerical, in the numerical technique of fitting that, then we obtain beautifully that the derivative is just nothing but for a V type function at the point where it is meeting 0.5, there's a step discontinuity is there. It is brought out very clearly. This is an excellent example. It's a tough problem to solve, but it is, showed this because you can see how it was hidden all this while. Okay. So now coming back to using spline, I hope you remember earlier. Now we have a set of points x0 to xn, and hi is my mesh interval, and I have the places where I am measuring yxi is the true value, yi is what I'm measuring. It is less than delta. There is some noise which is associated with it. And I have imposed this condition 1 by n minus 1. I have extracted it from a paper. So here to that previous this one, there will be a difference in the all the variables. Yi minus fx plus alpha into integral of x squared. That the what I shown by pink, this one, it is, this has to be minimized. Here only p is not there, one alpha is there. Doesn't matter that this number to this number, the ratio is 1 is to alpha, right? Now that is the kind of thing I have to judge, now obtain. Now, well, this is, I cannot avoid this mathematics, but I am highlighting you only this thing. The blue line indicates that's a polynomial, cubic polynomial, which is we are trying to interpolate on those xi's. Now, continuity condition of the second derivative involves all these equations, which you merely we can skip. And in the top, you can see the pink line, that is the continuity condition leads to certain system of equations. Now, the condition which we have used, namely that we have shown here in that equation number 1, pink line, that transforms to 2 alpha q alpha is equal to d minus 2 y minus a. So when you combine all that, then finally we solve it. Yes, we solve it. Initially, we take one value of alpha, and we have put one condition, yes, yes can be equal to 0.0002. That is how accuracy I want. Then you keep iteratively running. Okay, this solve this equation, set of equations, come back to the lowest minimum point, check my S value whether it is meeting my specification. So I keep moving around this, unless, as I seen here, this minimum value, whatever I have put for my instrument, if it is happening, then that value I throughput, and that is my spline which I have fit. Okay. Now that is how we have got these values. By the way, this plot which I have shown earlier, all this have been obtained by that way only. They are cubic spline fit only. That's why they are so good. Okay, so the algorithm is you select that minimum criteria which we have got, then start with the value of p, obtain the spline parameters. Then, I mean, spline parameters means we obtain the spline coefficients, all that, whatever is written in the blue line, A, B, and all that. Once we obtain, then check the value of S. Is not satisfying, you go back, you iterate the value of, you change the value of P to one direction, because from 0 to 1 only values can take. So you move it from in one direction till we obtain that desired yes. Fine. Here, one second. Here we are having, this is the polynomial. Instead of a combination, add one more criteria. This is what is called the cross validation technique of WABA, where the measurement yi is measured minus my fit, that should be minimum. Okay, this also you keep checking. If you do that, then the one approach is saying that P can be found out more accurate. The idea of all this is our this P, which we are having here in this equation. Yeah, in this equation, the P value is a quality, it is subjective to the requirement of the system which you want to fit. So these techniques have all come up because of that. Yeah. And discrepancy principle, which I was telling, it is that is, we know that sigma on the right side, the variance we are having knowledge. Then we try to minimize my fit f star with respect to the measurement, such a way that this is condition is met. This is a very famous condition given by one Russian mathematician, Morozov. Okay, now this is a paper which I published some time back, fast derivative in applied numerical mathematics. Now I just take this a few minutes more on this. I've used the X splines and I suggested two values. That is, a regularization value can be a preset variance, or I used the discrepancy principle and see the difference between these things. But basically, I am not using cubic spline, but I'm using X spline in that. Now on the top, you can have that polynomial of the cubic polynomial, and 110.2 is the continuity condition, which is generally associated with the cubic spline, if you are familiar with it. And 21.2, I say that's how the noise characteristics of the variance is actually there. Now, the X spline is basically has a third derivative discontinuity. And I take an inspiration from this paper, which I am citing as Hanke and Schircher. It's a very famous paper in this field. And there they have allowed that if the third derivative is continuity and alpha is positive, then we can always have one which can meet the goal of getting a reliable numerical differentiator. So I set that value alpha is equal to the variance. Fine, still the solution comes. The example which I take is a true function. I take up sine of 2 pi x into e power something I have not written. U is equal to x squared. Now over -2 and +2. Then I have added some uniform noisy data of also between -0.01 to +0.01. Random numbers I've chosen, and I have added the noise on the top of this function. Then I am trying to see how this thing behaves. That is, I have got two approaches. One is an approach where I have simply take the regularization value to be the variance, and where I use in an iterative way using the discrepancy principle. Now, when I take the fixed regularization value, that is my S4, you can see. S4 convolution spline is given in the star one. One second, please, sorry. Okay, now you can see the fixed value by S4 is not actually coming close to the true value. Okay, it doesn't coincide close to the true value, whereas a convolution spline in adaptive way, it goes close to it. But the most important part of this, which is dealt in that particular paper, is the number of computations largely come down. So if you want to make a fast calculation, and it is orderless actually. So if you want to make a fast computation, we can go about using the variance as the regularized parameter. And then we can solve it. It is quite fine. This is a standard example everybody takes. And you can get roughly the smoothness as well as the accuracy. Only thing is where that change of direction is happening, there you can see slightly the accuracy is poor. So this is as far as fixed regularization is concerned. So fixed regularization scheme, the p value is preset, and only one shot you obtain the spline parameters and you solve it. It is very fast. Okay. job is done. Whereas when you use any of these other techniques, namely you use the discrepancy principle or the cross validation technique or the Schoenberg range technique, all these are iterative, and you have to go till you get the values, all that is there. Now what is happening when you use that kind of approach here? When I adopted the discrepancy and the exact value, you can see it is going one over the other. Now this is not very surprising, because I have set a limit S is equal to that accurate value. Now both the combination of smoothness as well as the noise, till that time this P keeps on moving. So till you get the point where it is happening, it doesn't end. So finally you can see the X-spline fit. Although even X-spline also is much more computationally faster than the cubic spline, because the equation solution is much lesser one order. So if you do that way, this is the thing. Now one more second. Yeah, this is if anybody is interested in this field, I suggest you read this article, Heuristic Approach and Regularization Method by for Numerical Differentiation by this very nice paper, where why I am suggesting this particular paper. There are, from here you can get into know the history geography of numerical differentiation with when the data is having noise. He is also proposing one method, but he will also cover some of the what do you call the papers in the literature. And here he presents one plot, which is a very interesting thing. The blue is actually the now you can see the exact one is a black dot, and there are other methods which I have not mentioned. De Boer method is there, and discrepancy principle is there, and one L curve method is. These are all other techniques. Now you see how each fit is principles are working. They are all the methods have some advantages. But why I am putting this plot? Because all these have been discussed in this particular paper by Howe. Request anyone who is interested in this numerical differentiation, go through this paper first. It will lead you to many other papers. Okay, that's it. Then, so I sum up my this one. What I am trying to tell is, we saw that there are issues straight away using numerical scheme, adopting them when we want to take derivatives when the data having a noise. Okay, why? Because numerical differentiation, both analytically and numerically, we have seen is unstable and ill-posed. So being unstable, it automatically becomes ill-posed. It's okay. And we saw also some couple of applications straight away where, based on the position, and further we needed velocity to very important to decide certain things, and the position being measured by instruments were automatically having noise. We also saw what actually is a noise, why noise is happening, and the Gaussian distribution of the noise, which is very adaptable for smoothing approaches like least square approaches, including Fourier series, everything. Now, that was only smoothing the activity, noise, but not the derivative, which we are interested. It is one step more ahead. So when we solve numerical, we seek a numerical solution of the measured data with the noise, we have to use what is called the Tikhonov regularization, P, which is a minimizing the smoothness plus P times noise. Now, what is P? P is decided by various criteria which we have seen across various numerical methods, and these numerical methods, they devise a way of obtaining a qualitative derivative. Why I am saying qualitative is a yes, the parameter on the left side, how you minimize, it depends upon you. And we saw also some illustrations which were telling us what happens to this P, how it keeps P varies, what happens to the smoothness, what happens to the minimizing of the noise. So with the interplay of all this, and some schemes which are fast in obtaining the derivative, which compromise the what you call the fitness, but they obtain the smoothness. So all this we have seen. That is when we take the variance to be the regularization value, the smoothness is there, but the accuracy is slightly poor at some places. Now, and this is how I'm ending. So when you take the velocity and when it hits the pad, if the velocity, if it is obtained properly, it tells us to know whether it is hit the stump or missed. I hope you had something interesting in this lecture. Thank you very much. Madam?
Sir, yeah, thank you so much, sir. Thank you so much for your wonderful session on numerical differentiation of noisy data. Yeah, we have learned many interesting applications, sir. Thank you so much, sir. I hope participants gain more information from your session. So it was really interesting and informative session. Thank you once again, sir.
I can take a question also. That's why I kept.
Yeah, sir. Yeah. So participants, if you have any questions now, you can ask it, sir.
Sir, there is a question.
Yeah, please be loud, kindly.
Sir, when we say that the noise is different, we can differentiate the noise. So how we can minimize it with the differentiation?
That is what the topic is only about that. See, when there is a measurement and the measurement is from an instrument, automatically there is a noise added to it. So when we are having that, we saw that also. What actually happens when we differentiate directly, that we are differentiating the noise also. Differentiating the noise leads to an unstable event also. We saw some examples, and moreover, as a Volta, when we transform into a Volta integral equation, automatically we found that differentiation is not a well-posed problem, it is an ill-posed problem. So we simply use a smoothing technique. Smoothing technique is only one part of it. So that is, I'm sorry, when we talk about reduction of noise, least square acid atoms, it only one part of it. Basically, what we need is a smoothing technique, namely the double derivative has to be minimum. So this is what the essence of the entire thing is. We have to have the noise reduction as well as smoothing condition. Once you put smoothing into place, then you find your derivative is reasonably what you called worthy, and it is reliable. That's all I can say, because still this particular mathematics is not like it. S is minimum is decided by the person. So if yes, you keep it as 0.05 to that level, the derivative is smooth, as well as the noise has been reduced. So I hope I've answered you understood what I'm saying. So the numerical differentiation involves in taking the regularization parameter properly. Okay, you just see the paper which I have cited there, namely by Howe. They are very interesting. Why, although I have written a paper on this subject, I also refer to this. My paper was reviewed possibly by this person. You see this from this is a very nice paper, heuristic regularization method. It gives you what is the subject is all about, and many previous papers he has reviewed in it, and he has exposed them very nicely. Okay, I hope I have answered your question.
Yes.
Anything more?
Yes, sir. Any other questions from participants? Okay, sir. Okay, sir. Yeah. Actually, the session was very informative and interesting session, sir. Thank you so much, sir.
Thank you.
Yes, sir. Really, we learned something from this session, sir. Like So what are the applications? How can we incorporate? So everything, sir. Thank you so much, sir.
Yeah.
Yeah. Now I request Ms. Anupriya to conclude the session.
Thank you, sir, for this wonderful session, and it's on numerical method and its applications. I hope this session is really very helpful to the participants. And dear participants, now we will take 5 minutes break and resume at 11:40 a.m. for the second session. Thank you.